In the next few videos, I'd like to take some time to discuss rocket science and rocket propulsion, and hopefully we'll be able to work an example of a real-life rocket towards the end of the videos. Okay, so there's two basic ways to create motion. The first way is to use external mass, external mass, and using an external mass is kind of like when you are on a skateboard and you push off against a wall to move, or when you push off of the ground and you move. That's using an external mass to create motion. The second way, if you haven't already guessed it, is the internal mass. The internal mass. Internal mass. The internal mass. And the internal mass method basically just means that we have to carry all of our extra mass with us. So if I want to move on my skateboard, I have to carry, say, a 25-pound weight and throw it in the opposite direction. This will cause motion. You can go try this out in your backyard or in your driveway. It's a really great experiment. Now, when we use internal mass, the internal mass method, we usually use fluid, and this fluid has a special name. It's called the working fluid. The working fluid. And the working fluid is just a gas or a liquid. It can be either one, a gas or a liquid, that creates motion, that powers a machine. Basically, the working fluid powers a machine, and we can see that the best example of this in aerospace, the two best examples of these in aerospace, are jets and rockets. For jets, the working fluid is just jet fuel. It's just jet fuel, and this jet fuel burns in an oxygen-rich environment. So all we need to carry up with us is our jet fuel, and it just combusts with the oxygen, and it burns in the opposite direction of motion. But for rockets, on the other hand, we have to carry our fuel and our oxygen. We have to carry our fuel and our oxygen, which we'll call an oxidizer. An oxidizer. And an oxidizer is just an element that lets combustion happen, that allows for combustion. Our fuel, in most cases, is just going to be regular old refined kerosene. The examples that we're going to use, the fuel source is RP1. If you'd like to Google that for more information on that, you can. But it's basically just refined kerosene. And the oxidizer that we carry is just liquid oxygen. And the reason we have to carry our oxidizer with us is because in space we don't have an oxygen-rich environment like we did with our jet fuel. We have to carry it with us. Now, I'd like to take a minute to talk about the two main types of rocket motors, solids and liquids. So for our solid rocket motors, or SRMs for short, solid rocket motors, we can think about solid rocket motors as giant fireworks almost. Because in solid rocket motors, we cannot control them once we turn them on. We can have some level of control with the geometries that we use, but aside from that, we can't turn them off once we've turned them on. So let's just draw a solid rocket motor, and you'll see what I'm talking about. A solid rocket motor, this is the cylindrical solid rocket motor, and a solid rocket motor basically has propellant going down the sides of its walls. But there is an opening here, but they leave an opening on the inside so that when a spark is conducted up at the very top of the rocket, all of this propellant which is on the sides, right here, all of this is solid propellant with our oxidizer and our fuel source solidified. When our spark happens, all of our propellant burns from the inside out. So it burns outwards. And once it gets to the wall, there is no more propellant left, and you're done. In contrast to the solid rocket motor, the liquid rocket motor is a bit more precise, we could say. The liquid rocket motor, or LRMs. For liquid rocket motors, we have to carry up our fuel source just like we do in our SRMs and our oxidizer. But in the case of our liquid rocket motor, we have to store them in tanks since they're in a liquid state. So here is our chamber for our liquid oxygen, and here is our chamber for our kerosene, or RP1 for short. RP1 for short. And let's just scroll down a bit. And our liquid oxygen and our RP1 are carried to something called the combustion chamber, and I'll draw a combustion chamber right out here. A combustion chamber, which you'll have probably seen this shape before, this kind of hourglass-ish shape, and it's just and a combustion chamber. The top piece of this rocket nozzle, this is actually called a rocket nozzle. A rocket nozzle. And the only reason we use a rocket nozzle is to create a change in pressure and temperature, which we'll get to in a second. But going back to the liquid rocket motor, the reason we use tanks to store this is because it's in a liquid form, and we have to use some type of mechanism to get the liquid to our rocket nozzle, and we use turbo pumps for that. Turbo pumps. And turbo pumps are nothing more than pumps the size of V8 engines that just pump out liquid oxygen and RP1 at a rate that we tell them in advance, and they just carry our liquid oxygen and our RP1 down to the rocket nozzle, which is right over here. So once they get to the rocket nozzle, they get pre-mixed with something called an injector plate. And an injector plate is basically just this round plate that looks kind of like a shower head. It has a lot of holes in it, and it's basically just a shower head that premixes our RP1 and our liquid oxygen right before they catch on fire and combust. But once they combust, they're pushed into our combustion chamber. The top piece of our rocket nozzle is called the combustion chamber. And once they're pushed downwards towards our rocket nozzle, we can assume some things. We can assume that there's extremely high temperature going on. Extremely high temperature since it's combusting, and it's highly pressurized. But it's going pretty slowly, so it has a low velocity right now. A low velocity. But once our propellant gets to this choking point, that we call it a choking point. This right here is our choking point. Our choking point. And once our propellant gets here, all of our variables change somewhat. Our temperature and pressure decrease dramatically. Our temperature and pressure decrease, so we have a low temperature and pressure. A low temperature and pressure now. And we have a very high velocity now. We have a very high velocity. And we'll draw these lines of velocity. But this high velocity has a special name to it as well. This high velocity is called our exhaust velocity, or VEX for short, the exhaust velocity. And the exhaust velocity just means the speed at which our propellant is being ejected from our rocket nozzle in a given amount of time. The speed of our propellant. Now, The second variable I'd like to introduce is called the mass flow rate, or m dot. Now, the mass flow rate just tells us how much propellant is leaving the rocket nozzle in a given amount of time. So it has units of kilograms per second usually. Kilograms per second usually. Whereas our exhaust velocity that we looked at has units of meters per second. Meters per second. And we can combine these two variables and get ourselves a nice equation for thrust. And our thrust equation is as follows. Thrust is a force which is equal to our mass flow rate multiplied by our exhaust velocity. And since this condition is in free space, this is in free space, then we don't have to take into account atmospheric conditions, and it simplifies our thrust equation. And in the next video, we'll look at how we can implement this thrust equation a bit more effectively, and we'll do some examples with it.